Good morning, class. Today I'm in Raleigh, but we've pre-recorded the lectures. And so today, what are we going to talk about? Thank you. And, sorry, this week's lesson is periodic motion in waves. And what is today's lesson? Thank you. Okay, wave behavior. We're going to skip the quiz name, obviously, because I'm not here. So, we're going to talk about different properties of waves. The first of all is reflection. Reflection is, of course, the bouncing off of something from a surface. When waves arrive at the surface, the new material will absorb some of the energy, but it will also release some of that energy as well. All of the energy that it doesn't absorb will bounce off of it. And that energy will continue to move through the original medium. This is similar to the bouncing of a ball. When you drop a ball, and it comes back up, all of the energy that was released when I dropped it, that was potential energy, changed into kinetic energy as it was falling down. But the problem is when it got to the ground and it hit, it reflected. Some of the energy that had been potential was absorbed by the ground, and it wasn't able to come up as high as my hand when I dropped it because it didn't have as much energy as it did before. And so this is like a wave pounding into a shoreline. Same thing. Some of that energy will be absorbed, other parts of that energy will be reflected. The law of reflection is the reflected angle of the reflected wave is equal to the incident angle. What that means. And this is perhaps best shown through light rather than through, say, an ocean wave. If we have a mirror and we have a beam of light or a ray of light coming in at 45 degrees, that ray is going to bounce off at what degree? At 45 degrees. So, this is the incident angle, and this is reflected angle. Incident meaning it's the incident that occurs to create the reflection, and reflected meaning it was reflected. So that's pretty simple. Specular reflection is the clear image from a mirror. It is involved in seeing any object that doesn't emit its own light as it is through sunlight reflecting off of objects so that we can see them. And really that is how we see. We have light coming down from the sun. It is absorbed by entities, by objects around the world, but it does reflect some of that light. That reflected light is what we see. Any light that is absorbed, we don't see. So for instance, black, it absorbs all the light. So that's why it's black. There's no light coming to us from something that is black. If we have white, that means it is releasing all of the light. And so we have the full spectrum coming towards us, and that blends together as white. Diffuse reflection is when light is scattered, and that, like a dull note, like if you scratch or if you tap a whiteboard as opposed to playing an instrument, one end will produce a dull note, the other one will produce a precise note that is actually a musical sound. Same thing for light. Diffuse light is that dull note. except in terms of light. Specular reflection is a clear image created by electromagnetic waves. Refraction, this is a little bit different. So instead of bouncing off, it is going to go through an object. This is when light bends as it enters the medium. We can see this if we put a laser up to some sort of glass, and we can see how the glass bends the light. We can also see it if we have a glass of water, because both the glass and the water will end up bending the light in certain ways. You can see this when you look through a fish tank at the fish. What you see is not a realistic image, at least a completely realistic image of what is actually going on inside the fish tank, because the light is bent in certain ways. When a wave arrives at a surface, some of the energy goes into the new material, and refraction occurs, or the bending of a wave occurs, because the wave moves at a different speed in a different medium. Snell's law states that, it describes how the wave changes direction as it moves into a new medium. Ocean waves are refracted by the ocean bottom that turn the waves parallel to the shore. And so you can't see it if you're sitting on the shore because you don't have the vantage point to do so. But if you looked at a larger scale, the waves would actually be moving at an angle towards the shore instead of straight upon it. Diffraction. This is the bending of waves around an obstacle or through an opening. It's a little bit of an interesting concept, more complex in reflection and refraction. This can be shown by a rock near the shore, and the waves have to move around the rock as they're getting pushed towards the shore. The interaction between the wave and the obstacle or the edges of the opening causes the wave to change direction, and light can be diffracted if the obstacles are small enough. Diffraction grating is having thin lines etched in them as diffract lasers. Tumbelows. These are landforms that connect islands with the shore, making it realistically a peninsula. They develop because of the refraction and diffraction of the ocean waves, and as the waves approach the shore, they refract toward the island from seaward. The water diffracts around the island, and the waves that move behind the island are slower, allowing for more deposition of sediments connecting the island to the mainland. Interference. This is how sound negating headphones work. The interference is a combining of waves where they overlap, and there's two different types. There is constructive interference when the waves come together, and they come together step by step. They're in sequence with one another. So you have one wave going like this. Remember, it's sinusoidal. Another wave coming like this. You see the troughs are where the ever troughs are. The peaks are where the ever peaks are, where the crests. So the crests get added together and become one big crest. The troughs get added together and become one deep trough. And so it just accentuates everything in the wave and it amplifies it. Now, destructive interference is how noise canceling headphones work. Instead of having the two waves be in sync with each other, they are directly opposite. So instead of having a crest here, we're going to have a trough. Instead of having a trough here, we're going to have a crest. And it goes up. Sorry, my drawing is a little bit off. And it goes opposite all the way through. So when we get a trough and a crest together, it becomes a flat line. If we get a crest and a trough together, it becomes a flat line. And so on for the entire wave. And just becomes flat, which results in no wave. In reality, in normal nature, what happens is a mix of constructive and destructive interference, which can amplify sounds depending on the environment, or that can dampen sounds depending on the environment. That's why if you are working on designing a lecture hall or a orchestra hall, somewhere where concerts or plays are being given, the science of acoustics is very important because you always want to provide constructive interference throughout the room for the area where the play or the opera is occurring, or the orchestra is playing. And you want to provide destructive interference for where the audience sits at. So the audience is muted and the performers are amplified. Standing waves. These are waves that move even though the locations of the crests and troughs appear to be stationary. Similar to the longitudinal waves we talked about yesterday. Two identical waves of a specific wavelength moving through a medium in opposite directions can cause a standing wave. The length of the medium must be a multiple of 1/2 of the wavelength. Nodes are 4 locations that don't seem to move at all, and antinodes are the location of the crests and troughs that are the points of maximum motion. Doppler effect. If any of you have seen an ambulance driving by and notice the pitch of the ambulance's siren is different from when it's coming towards you to when it's going away from you, that is because Christian Doppler's effect, which he described in 1842. What happens is, as an ambulance is coming to you, the waves that it is sending out pack in on one another. So you got the ambulance, you got you, it's sending out sound waves. But because it's coming closer and closer to you, the frequency of the sound waves gets higher and higher and higher. Because as it's coming to you, the rate at which it's emitting the waves stays the same, but the distance between those waves doesn't. It gets shorter. So it has the ability to send them quicker to you when it's closer than when it is farther away. Frequency in sound also means pitch. So if you play something like an A note, that's going to have a lower frequency than a B note, which is a higher frequency. Same thing, if a B note has a lower frequency than a C, C has a lower frequency than a D, and all of these steady inclinations in pitch have higher sounding noises, or higher sounding musical notes. So as it gets closer and closer to you, the pitch rises. When it is the opposite, and the ambulance is moving away from you, it's still producing that noise, but it's coming further back. The more it moves away from you, the more time it takes for that sound to move from here to your ears, which means that there's a lower frequency of waves hitting your ears, resulting in lower pitch. So if you had a G note on a guitar or on a piano, that would be like playing a F note, and then playing an E note, then playing a D note, then a C, then a B, and then finally an A. The Doppler effect occurs with all waves and has numerous applications, including with satellites. That is how we figure out where hurricanes are moving is through Doppler satellites. Weather radar can now determine from how storms are moving relative to the radar site because of how the frequencies change with the Doppler effect. Police use the Doppler effect in order to tell if you're speeding. And that's it. Thank you.